Welcome to Whispering Universes channel, where tonight we witness the most tender miracle in all of creation. In the vast cosmic darkness that surrounds us, something miraculous stirs. Between the ancient stars that already shine and the black depths of interstellar space, you are about to witness the universe giving birth. From the coldest, emptiest reaches of space, regions so sparse that a handful of atoms float where Earth's atmosphere packs trillions, comes the warmest, most radiant light. Tonight, we attend the quiet delivery rooms of creation itself, where stars emerge from darkness with the patience of geological time and the inevitability of love. Imagine drifting through space at this very moment, your consciousness floating between the stars. Around you stretches what appears to be perfect emptiness, a vacuum so complete that ancient astronomers called it the void. But your eyes deceive you. This apparent nothingness teems with the raw materials of future suns. Invisible clouds of hydrogen and helium, the primordial inheritance from the universe's birth, drift like cosmic fog through regions larger than entire solar systems. These are the stellar nurseries, molecular clouds so vast that light requires years to cross them, yet so gossamer that if you could compress one down to Earth's density, it would weigh less than a feather. Within their frigid embrace, temperatures hover just degrees above absolute zero. Here, in conditions more hostile to life than the deepest ocean trenches or highest mountain peaks, the universe performs its most essential act of creation. Star formation is cosmic reproduction in its purest form. Like all births, it begins in darkness and emerges into light. The process requires time, not the hurried minutes of human birth, but millions of years of patient gestation. Yet, the result is equally miraculous. From cold, dark clouds emerge nuclear furnaces that will burn for billions of years, creating the heavy elements that make planets possible and the energy that makes life inevitable. Gravity becomes the gentle midwife in this cosmic delivery. Unlike the violent forces we associate with astronomical events, supernovae, explosions, black hole collisions, the Big Bang itself, star formation proceeds with quiet inevitability. Gravity works patiently, nudging individual atoms closer together over countless millennia until mere proximity becomes gravitational attraction. Attraction becomes collapse, and collapse becomes ignition. The story begins with hydrogen, the universe's first and simplest gift to itself. Created in the first minutes after the Big Bang, when the cosmos was still hot enough to forge atomic nuclei from pure energy, hydrogen atoms have been waiting 14 billion years for their moment of transformation. They drift through space, 1 or 2 atoms per cubic centimeter, outnumbered by human thoughts yet collectively comprising the primary ingredient of every star that will ever shine. But hydrogen alone cannot birth a star. The universe requires precise conditions, temperature thresholds that must be crossed, pressure barriers that must be overcome, and density requirements that push the very limits of what space can contain while remaining space. These conditions emerge not through cosmic planning but through the beautiful chaos of gravitational dynamics, where random motions and chance encounters create pockets of possibility scattered throughout the galaxy. Nuclear fusion becomes the star's first breath, the moment when hydrogen transforms into helium and mass becomes energy, according to Einstein's most famous equation. This nuclear awakening releases energy that will outlive human civilizations, powering stellar hearts for timescales that dwarf geological epochs. The energy emerges not as sudden explosion but as sustained burning, nuclear fires that will warm planetary surfaces and enable the chemistry of life across cosmic distances. These timescales stretch beyond human comprehension, yet understanding them reveals something profound about existence itself. While human lives unfold across decades, stellar births require millions of years. While human generations span centuries, stellar lifetimes encompass billions of years. The stars that warm our nights were born when the universe was young, their light carrying stories of cosmic adolescence across distances that reduce our solar system to insignificance. Tonight, as you listen to these words, new stars are stirring in molecular clouds scattered throughout our galaxy. In the constellation Orion, visible on winter nights, stellar nurseries actively deliver new suns into existence. In the Eagle Nebula, gravity sculpts towering pillars of creation where embryonic stars await their nuclear awakening. In regions invisible to human eyes but revealed by infrared telescopes, The universe continues its ancient work of transforming darkness into light. Let us drift toward these cosmic cradles where light is born, where the universe whispers its deepest secrets about creation, patience, and the inevitable emergence of complexity from simplicity. The story of stellar birth is ultimately our story, for we are made of material forged in the nuclear hearts of stars that lived and died before our sun was born. Understanding their birth helps us understand our own cosmic ancestry, our place in the vast story of cosmic evolution that connects the Big Bang to the present moment. As your breathing slows and your consciousness drifts towards sleep, prepare to witness the gentlest miracle in the universe, the quiet birth of stars, from dust to light. In the darkness between stars lies the universe's most carefully guarded secret. What appears to be empty space contains vast clouds of matter so tenuous they make Earth's atmosphere seem thick as concrete, yet so extensive they dwarf our entire solar system. These are the molecular clouds, cosmic wombs where stars spend their first millions of years in gestation. Picture yourself floating in the Orion Nebula, that familiar winter constellation whose sword contains one of the galaxy's most active stellar nurseries. Around you stretches what astronomers call a giant molecular complex, a region of space containing enough material to birth thousands of suns. Yet, if you reached out your hand, you would encounter fewer atoms than exist in the best laboratory vacuum chambers on Earth. The cloud's density averages just a few hundred particles per cubic centimeter, sparse beyond human comprehension, yet rich enough to nurture new stars. The temperature here hovers at -440 degrees Fahrenheit, just 20 degrees above absolute zero. In this cosmic deep freeze, even hydrogen, the universe's most abundant element, exists not as individual atoms, but as molecules, paired hydrogen atoms clinging together for warmth in the interstellar cold. These H2 molecules become the fundamental building blocks of future stars, the raw material that gravity will eventually coax into nuclear ignition. This represents one of space's most beautiful paradoxes. Regions that appear utterly barren contain the seeds of cosmic fertility. Dark nebulae, those mysterious patches of apparent emptiness that early astronomers thought were holes in the star fields, are actually stellar nurseries so dense with dust that they block the light of background stars. What appears as cosmic emptiness is actually cosmic fullness, pregnant clouds awaiting the moment of gravitational awakening. The Orion Nebula exemplifies nature's cosmic delivery room in action. Within its glowing gas clouds, captured beautifully by space telescopes, new stars announce their births with brilliant jets of material streaming into space. These Herbig-Haro objects, named after their discoverers, mark where stellar infants clear away their birth material like cosmic cries announcing new arrivals. The nebula's familiar trapezium of bright stars, visible to naked eyes as Orion's sword, represents stellar siblings born from the same molecular cloud, their nuclear fires now illuminating the remnants of their shared cradle. Infrared telescopes reveal the hidden drama unfolding within these apparent voids. Our human eyes, evolved to see sunlight reflected from Earth's surface, cannot penetrate the dust that permeates molecular clouds. But infrared radiation, heat energy, passes through dust like visible light through clear glass. When astronomers turned infrared eyes toward regions of apparent emptiness, they discovered bustling stellar maternity wards hidden from optical view. The chemistry within these stellar nurseries operates on scales both intimate and vast. While the overall cloud spans dozens of light years, the actual birth of individual stars begins in dense cores no larger than our solar system. Within these cores, temperatures remain so low that exotic chemistry becomes possible. Water, ice, carbon monoxide, snow, and frozen methane coat, microscopic dust, grains like frost on winter windows. These ice mantles create chemical laboratories, where complex organic molecules form through processes impossible in Earth's warm environment. The dust grains themselves tell stories of cosmic recycling. Each particle represents material ejected from dying stars, carbon soot from ancient red giants, silicon and iron crystals from long-dead supernovae. These stellar ashes become the condensation nuclei around which new stellar systems will form, connecting the death of old stars with the birth of new ones in an endless cycle of cosmic renewal. Giant molecular complexes represent the largest coherent structures in our galaxy aside from the galaxy itself. The Orion complex spans over 300 light-years, containing dozens of stellar nurseries at various stages of activity. Some regions actively birth new stars, their warmth triggering cascade effects in neighboring clouds. Other regions remain dormant, waiting for triggering events that may come from supernovae explosions, collisions with neighboring clouds, or the gravitational stirring of passing spiral arms. Within these vast structures, turbulence creates a hierarchy of smaller clouds nested within larger ones like Russian dolls. Supersonic winds, driven by the energy of newly formed stars, carve bubbles and cavities in the surrounding material. Magnetic fields, though weak by Earth standards, exert profound influence over the movement of charged particles and dust grains. The result is a complex ecosystem where stellar birth triggers stellar birth, where the energy of new stars shapes the environment for future generations. The molecular clouds represent cosmic patience in its purest form. Unlike the violent events that dominate astronomical headlines, supernovae, gamma-ray bursts, black hole mergers, stellar nurseries operate on timescales that make geological processes seem rapid. Individual molecular clouds persist for tens of millions of years, slowly evolving as gravity gathers their material into increasingly dense concentrations. Within these timescales, multiple generations of stars can form, each cohort altering the environment for their successors. Dark nebulae, scattered throughout our galaxy, mark the locations of these invisible stellar factories. The famous Horsehead Nebula in Orion appears as a dark silhouette against background starlight, its distinctive shape carved by stellar winds from nearby hot stars. The Coalsack Nebula, visible to Southern Hemisphere observers as a dark patch in the Milky Way, contains enough material to birth hundreds of sun-like stars. These apparent voids actually represent some of the most fertile regions in our galaxy. As we drift through these cosmic nurseries in our imagination, we witness the universe's most fundamental creative act. From apparent emptiness comes the material basis for every complex structure in the cosmos: planets, life, consciousness itself. The molecular clouds represent the universe's commitment to creating complexity from simplicity, order from chaos, light from darkness. In their patient embrace, the seeds of future solar systems await the gravitational awakening that will transform cold, sparse gas into the nuclear furnaces that power cosmic evolution. Gravity operates as the universe's most patient sculptor, working not with sudden violence, but with inexorable gentleness across millions of years. In the molecular clouds where stars are born, gravity's influence begins almost imperceptibly, a slight preference for atoms to drift toward regions of marginally higher density rather than lower. Yet this subtle bias, amplified across cosmic time, transforms tenuous gas clouds into blazing nuclear furnaces. The story begins with what astronomers call the Jeans instability, named after British physicist James Jeans, who first calculated the critical conditions for gravitational collapse in the early 1900s. Within any gas cloud, random thermal motions normally prevent gravitational gathering. Molecules move too quickly for gravity to gather them together. But when a cloud region grows large enough and cool enough, gravity finally gains the upper hand over thermal pressure. The critical mass required depends on temperature and density, but typically requires material equivalent to several sun masses concentrated within a few light years. This transition represents one of nature's most elegant phase changes. Below the critical threshold, thermal pressure dominates and the cloud remains stable. Above it, gravity inexorably wins, and collapse becomes inevitable. The boundary between these regimes, the Jeans mass, determines whether a cloud region will remain diffuse gas or become a stellar cradle. Understanding this threshold allows astronomers to predict where and when stars will form throughout the galaxy. Once gravitational collapse begins, the process follows patterns as predictable as water flowing downhill, yet as complex as weather systems. The cloud doesn't collapse uniformly, but fragments into multiple dense cores, each destined to become an individual star or stellar system. Turbulence within the cloud creates eddies and currents that concentrate material into knots of higher density. These knots become gravitational seeds, each growing by accreting surrounding material like cosmic whirlpools drawing in everything nearby. The battle between turbulence and gravity shapes stellar birth statistics across the galaxy. Turbulent motions, driven by stellar winds, and supernova explosions from previous star formation episodes, resist gravitational collapse and prevent runaway star formation. Without turbulence, molecular clouds would collapse catastrophically, converting all their material into stars within a few million years. Instead, turbulence ensures that star formation proceeds gradually, with only a small percentage of cloud material becoming stars each million years. Magnetic fields add another layer of complexity to gravitational collapse. Though weak by laboratory standards, millions of times weaker than a refrigerator magnet, these fields exert significant influence over the charged particles and dust grains that comprise molecular clouds. Magnetic pressure provides additional support against gravitational collapse, requiring higher densities before stars can form. The fields also channel the flow of collapsing material, creating preferred directions for matter infall and helping explain why many stars form in elongated structures rather than spherical clusters. Shockwaves from nearby massive stars or supernova explosions can trigger gravitational collapse in otherwise stable cloud regions. These compression waves propagate through interstellar space like sonic booms, increasing density and pressure in molecular clouds they encounter. The additional compression can push borderline regions above the gene's threshold, initiating star formation in clouds that might otherwise remain dormant for millions of additional years. This triggered star formation creates spatial and temporal correlations in stellar birth. Regions of active star formation tend to produce multiple generations of stars in cascade effects that can persist for tens of millions of years. Computer simulations reveal the intricate choreography of gravitational collapse with stunning detail. Modern supercomputers can model the collapse of molecular cloud cores from initial conditions through the formation of protostellar disks, tracking the interplay between gravity, thermal pressure, magnetic fields, and rotation. These simulations show how initially smooth density distributions develop complex structure through gravitational amplification of tiny initial fluctuations. The simulations also reveal why binary and multiple star systems form so commonly. As collapsing cores fragment due to gravitational instabilities, they often split into two or more dense regions that orbit around their common center of mass. These proto-binary systems then evolve together, each component accreting material from their shared envelope. The final result can be binary stars in close orbits, wide binary pairs separated by thousands of astronomical units, or complex multiple star systems with three or more components. Gravitational collapse proceeds through distinct phases, each governed by different physical processes. Initial collapse occurs in freefall, with material accelerating inward under its own gravity. As density increases, the mean free path of particles decreases until collisions become frequent enough to establish local thermal equilibrium. Further collapse heats the core until thermal pressure begins to resist gravitational compression, slowing the collapse rate and establishing the first hydrostatic equilibrium. The efficiency of star formation reflects gravity's gentle approach to cosmic construction. Only about 1% of molecular cloud material ultimately becomes stars. The rest is dispersed by stellar winds and radiation pressure from newly formed massive stars. This low efficiency ensures that star formation proceeds gradually across galactic history rather than consuming all available material in a single burst. The gradual pace allows for the chemical enrichment of interstellar space as successive stellar generations live, evolve, and die, adding heavy elements to the cosmic mix. Gravity's role in star formation exemplifies how simple physical laws create complex outcomes when operating across vast scales of space and time. The same gravitational attraction that governs planetary orbits and apple falls operates in molecular clouds to gather diffuse material into dense concentrations capable of nuclear ignition. Yet the outcomes depend sensitively on initial conditions. Small differences in density, temperature, or magnetic field strength can determine whether a cloud region becomes a massive star cluster or remains forever dormant. As gravitational collapse progresses from initial instability through fragmentation to core formation, we witness the universe transforming potential energy into kinetic energy and ultimately into the thermal energy that will power nuclear fusion. Each step in this process follows physical laws discovered in terrestrial laboratories, yet the combination produces phenomena unlike anything possible on human scales. Gravity becomes the cosmic midwife, gathering cosmic raw materials and preparing them for the nuclear awakening that transforms cold gas into brilliant stars. As gravitational collapse accelerates within stellar nurseries, something remarkable begins to happen. The cold material that has drifted through space for millions of years starts to warm. This heating represents one of physics's most fundamental energy conversions, gravitational potential energy, transforming into thermal motion as matter falls inward under its own weight. The process follows laws discovered by 19th century physicists, yet creates conditions unlike anything achievable in terrestrial laboratories. The heating begins gradually, almost imperceptibly. In the early stages of collapse, when densities remain relatively low, the infalling material can radiate away thermal energy faster than gravitational compression generates it. The core actually cools slightly during initial collapse, maintaining temperatures near the cosmic background temperature of just a few degrees above absolute zero. Atoms and molecules move sluggishly in this frigid environment, their thermal velocities insufficient to prevent gravitational gathering. But as collapse continues and density increases, the ability to radiate heat away decreases dramatically. The deepening gravitational well traps thermal radiation more effectively, while the increasing density makes the cloud more opaque to its own heat emission. At this critical transition, temperature begins its inexorable climb toward the millions of degrees required for nuclear fusion. The transformation from cold cloud to hot protostar follows the virial theorem, a fundamental relationship between kinetic and potential energy in gravitationally bound systems. The virial theorem predicts that exactly half the gravitational potential energy released during collapse becomes thermal energy, while the other half radiates away into space. This means that as material falls deeper into the gravitational well, its temperature must increase proportionally. For a collapsing stellar core, temperatures rise from near absolute zero to thousands of degrees during the main accretion phase, then millions of degrees as the core reaches stellar densities. The mathematical precision of this relationship allows astronomers to predict stellar core temperatures based solely on mass and radius measurements. The timeline for this heating process spans roughly 1 million years for a Sun-like star, extraordinarily rapid by astronomical standards, yet leisurely compared to human timescales. During this period, known as the Kelvin-Helmholtz contraction phase, the protostar derives all its energy from gravitational collapse rather than nuclear fusion. Lord Kelvin first calculated this timescale in the 1800s, ironically concluding that the Sun could be no more than a few million years old, a calculation that troubled 19th century geologists who needed much longer timescales for Earth's geological evolution. Not every collapsing cloud core successfully becomes a true star. Objects with insufficient mass, less than about 8% of the Sun's mass, cannot achieve the central temperatures required for sustained hydrogen fusion. These failed stars, called brown dwarfs, represent stellar stillbirths that heat up during initial collapse, but gradually cool over billions of years, without ever igniting nuclear fires. They glow dimly in infrared light from their residual heat, cosmic embers that remind us of the precise conditions required for stellar birth. The minimum mass for stellar ignition reflects the fundamental physics of nuclear fusion. Hydrogen nuclei carry positive electric charges that strongly repel each other. Only at temperatures exceeding 10 million degrees do hydrogen nuclei move fast enough to overcome this electrical repulsion and fuse together. Lower mass objects simply cannot compress their cores to these extreme temperatures, condemning them to eternal cooling rather than nuclear awakening. As protostellar cores heat up, their internal structure becomes increasingly complex. Temperature and density no longer remain uniform throughout the collapsing object. Instead, steep gradients develop with the hottest, densest material concentrated at the center and cooler, less dense material in the outer regions. Heat transport from the core to the surface becomes increasingly important, with photons carrying thermal energy outward through random warp processes that can take thousands of years to complete. Opacity, the resistance of material to the passage of radiation, plays a crucial role in determining internal temperature structure. As density increases during collapse, the material becomes increasingly opaque to its own thermal radiation. This opacity traps heat in the core, driving temperatures even higher and accelerating the approach to nuclear ignition conditions. Different materials contribute to opacity at different temperatures. Dust grains dominate at low temperatures, while ionized atoms become the primary opacity source at high temperatures. The first hydrostatic equilibrium marks a critical milestone in stellar birth. When thermal pressure generated by gravitational heating finally balances the inward pull of gravity, runaway collapse ends, and the protostar achieves temporary stability. This equilibrium occurs when core temperatures reach about 2000 degrees Kelvin, hot enough to dissociate hydrogen molecules and ionize some atoms, but still far short of nuclear fusion temperatures. The protostar has become a true stellar object, supported by internal pressure rather than merely falling inward under gravity. This initial equilibrium proves temporary because the protostar continues losing energy through surface radiation. To maintain internal pressure support, the core must contract further and heat up more. This slower, quasi-static contraction continues for millions of years, gradually increasing central temperature and density until nuclear fusion becomes possible. The protostar spends this period in a delicate balance, contracting just fast enough to replace radiated energy through gravitational heating. Different stellar masses follow distinctly different evolutionary paths during this phase. Low-mass protostars contract slowly and maintain relatively cool surface temperatures, appearing as red objects in astronomical images. High-mass protostars evolve more rapidly and achieve higher surface temperatures, glowing blue-white even before nuclear ignition. The most massive protostars evolve so quickly that they may begin nuclear fusion while still accreting material from their birth clouds. Stellar rotation complicates the heating process in important ways. As protostars contract, conservation of angular momentum causes their rotation rates to increase dramatically, similar to figure skaters spinning faster when they pull in their arms. Rapid rotation creates centrifugal forces that resist gravitational collapse, particularly in the equatorial regions. This effect can slow the heating process and influence the final stellar properties. The stirrings of warmth in collapsing stellar cores represent the universe's preparation for nuclear awakening. Each degree of temperature increase brings the protostar closer to the threshold where hydrogen nuclei can overcome electrical repulsion and fuse together, releasing the energy that will power stellar evolution for billions of years. This gradual heating process transforms cold, dark clouds into the brilliant nuclear furnaces that illuminate galaxies and enable the complex chemistry required for planetary formation and biological evolution. Within the frigid embrace of stellar nurseries, chemistry takes on forms impossible in the warm environments familiar to terrestrial life. At temperatures just above absolute zero, exotic reactions proceed that would never occur on Earth, creating molecular complexity from the universe's simplest ingredients. These cosmic laboratories operate on scales spanning light years, yet their most intricate chemistry occurs in microscopic ice mantles, coating dust grains no larger than particles of cigarette smoke. The foundation of stellar nursery chemistry lies in molecular hydrogen formation, the universe's most important chemical reaction. Individual hydrogen atoms, created in the first minutes after the Big Bang, cannot directly combine to form H2 molecules in the cold emptiness of space. The process requires a surface catalyst, where atoms can temporarily stick and encounter each other. Dust grains provide these essential surfaces, their crystal lattices offering temporary parking spots for hydrogen atoms until chance encounters allow molecular bonding. This grain surface chemistry proceeds with exquisite delicacy. When a hydrogen atom strikes a dust grain traveling at typical interstellar velocities, it must lose exactly the right amount of energy to stick without immediately bouncing away. Too much energy, and the atom escapes back into space. Too little, and it never approaches close enough to bond. The grain surface must act as both trap and matchmaker, holding atoms long enough for chemistry while allowing products to escape when reactions complete. Carbon monoxide emerges as the stellar nursery's most reliable thermometer. This simple two-atom molecule forms readily in the interstellar environment and emits radiation at specific wavelengths that depend sensitively on temperature. Radio telescopes can detect CO emission from molecular clouds throughout the galaxy, mapping temperature variations with precision impossible through other methods. The CO observations reveal the intricate thermal structure of stellar nurseries, showing how gravitational heating creates temperature gradients that drive chemical differentiation. Complex organic molecules form through step-by-step chemistry on dust-grained surfaces, building molecular complexity one atom at a time. Water ice provides the foundation for much of this chemistry, coating grain surfaces with frozen H2O that can trap other molecules and facilitate chemical reactions. When ultraviolet radiation from nearby stars penetrates the cloud, it breaks chemical bonds and creates reactive fragments that recombine into new molecular species. This radiation-driven chemistry creates methanol, formaldehyde, acetaldehyde, and even more complex organic compounds that would be familiar to biochemists. The ice mantles themselves tell stories of environmental history. In the coldest cloud regions, where temperatures hover near 10 degrees above absolute zero, carbon monoxide freezes directly onto grain surfaces. Water ice forms at slightly higher temperatures, creating layered structures with CO trapped beneath H2O. When stellar heating begins during protostar formation, these ices sublimate in reverse order of their formation, releasing chemical traces that reveal the thermal history of stellar birth regions. Isotope ratios provide fingerprints of formation conditions that persist throughout stellar evolution. During the cold chemistry of molecular cloud cores, different isotopes of the same element behave slightly differently in chemical reactions. Carbon-13, the heavy isotope of carbon, tends to concentrate in carbon monoxide molecules relative to carbon dioxide. These isotopic preferences, established during the cold chemistry phase, become locked into the stellar birth environment and eventually incorporated into planetary systems that form around new stars. Chemical differentiation occurs as gravitational collapse proceeds and temperature gradients develop within protostellar cores. Molecules with different binding energies freeze out of the gas phase at different temperatures, creating distinct chemical zones. Near the center, where temperatures climb above 100 degrees Kelvin, only the most refractory materials remain in solid form. Further out, carbon monoxide ice sublimates and returns to the gas phase. At the greatest distances, water ice can exist in solid form, creating snow lines that will later influence planetary formation processes. Deuterium chemistry provides a sensitive probe of stellar nursery conditions. This heavy isotope of hydrogen participates in chemical reactions at rates that depend strongly on temperature. In the extreme cold of molecular cloud cores, deuterium enhancement can reach levels thousands of times higher than the cosmic average. These enrichments become incorporated into the stellar birth environment and provide chemical fossils that astronomers can detect in newly formed planetary systems, revealing their formation conditions millions of years after the fact. The cosmic kitchen operates with ingredients established by nuclear processes in previous stellar generations. Hydrogen and helium, created during Big Bang nucleosynthesis, provide the primary raw materials. Carbon, nitrogen, and oxygen, the basis for most organic chemistry, were forged in the nuclear cores of ancient stars and dispersed into space when those stars died. Silicon and iron, essential for dust grain formation, originated in massive stars that ended their lives in supernova explosions. Each molecular cloud thus contains a chemical heritage spanning billions of years of galactic evolution. Magnetic fields influence chemistry by controlling the motion of charged particles and ions. While dust grains remain electrically neutral and move freely through space, ionized atoms follow magnetic field lines. This effect creates chemical separation, where different molecular species concentrate in regions of different magnetic field strength. The result is chemical gradients that reflect the magnetic structure of stellar nurseries, adding another layer of complexity to the cosmic chemistry puzzle. Shockwaves from stellar winds and supernova explosions drive high-energy chemistry that complements the gentle grain surface reactions. When these shocks pass through molecular clouds, they heat gas to thousands of degrees and compress it to higher densities. Under these conditions, gas phase chemistry proceeds rapidly, creating molecular species that cannot form in the cold, low-density environment of undisturbed clouds. The shock chemistry adds reactive species that can participate in subsequent grain surface reactions, enriching the overall molecular complexity. Timescales for chemical evolution span the entire stellar formation process. Simple molecules like molecular hydrogen and carbon monoxide form relatively quickly, reaching chemical equilibrium within thousands of years. Complex organic molecules require longer timescales, building up gradually through multi-step reaction chains that may require millions of years to complete. The most complex molecules detected in stellar nurseries contain dozens of atoms and represent chemical evolution spanning multiple stellar formation episodes. As we witness chemistry proceeding in the cosmic kitchen of stellar nurseries, we observe the universe creating molecular complexity from its simplest ingredients. These chemical processes establish the raw materials from which planetary systems will form, determining the molecular inventory available for subsequent chemical evolution on planetary surfaces. The exotic chemistry of stellar birth regions thus connects the nuclear processing in stellar cores to the biological chemistry that emerges billions of years later on suitable planetary worlds. The moment of protostellar awakening marks one of the universe's most profound transitions, when a collapsing cloud core first achieves the delicate balance between gravitational compression and internal pressure support. This hydrostatic equilibrium transforms a freely falling mass of gas into a genuine stellar object, marking the birth of a protostar that will spend the next million years preparing for nuclear ignition. The first hydrostatic core forms when central temperatures reach approximately 2000 degrees Kelvin, hot enough to dissociate molecular hydrogen into individual atoms and ionize some of those atoms into free protons and electrons. This dissociation and ionization absorbs enormous amounts of thermal energy, temporarily halting the temperature rise and allowing pressure forces to catch up with gravitational compression. The result is a temporary equilibrium where inward gravitational forces exactly balance outward pressure forces. This initial core remains relatively small, typically about the size of Earth's orbit around the Sun, yet contains enough material to eventually become a star. The core density at this stage reaches about 1/10,000th the density of water, still incredibly tenuous by terrestrial standards, but representing a dramatic increase from the initial molecular cloud density. Temperature and pressure conditions in the core create an environment unlike anything found elsewhere in the universe. Too hot for molecules to survive, yet too cool for nuclear reactions to proceed. As the first core achieves equilibrium, the surrounding envelope continues its gravitational collapse, raining material onto the core surface at rates of roughly 1 Earth mass per 1,000 years. This accretion process gradually increases the core mass and central pressure, driving temperatures ever higher toward the nuclear ignition threshold. The accretion energy released as material falls onto the protostar provides the luminosity that makes these objects detectable to infrared telescopes. Protostellar disk formation occurs naturally during this phase through conservation of angular momentum. The original molecular cloud core possessed some initial rotation, perhaps acquired through galactic shear forces or turbulent motions within the parent cloud. As material collapses inward, this rotation spins up dramatically, just as figure skaters accelerate when they pull in their arms. The increasing rotation creates centrifugal forces that resist collapse in the equatorial plane while allowing continued collapse along the rotation axis. The result is a flattened disk of material orbiting the central protostar, with new material from the collapsing envelope continuing to fall onto both the star and disk. These circumstellar disks extend from the stellar surface outward for hundreds of astronomical units, containing significant fractions of the total system mass during the early accretion phase. Within these disks, the seeds of future planetary systems begin their formation process, while the central star continues its growth toward main sequence ignition. Jets and outflows emerge as dramatic signatures of protostellar birth, creating some of the most spectacular phenomena in stellar nurseries. As material from the disk accretes onto the protostar, complex magneto-hydrodynamic processes channel some of the infalling matter into high-velocity jets that shoot outward along the stellar rotation axis. These jets travel at speeds of hundreds of kilometers per second, carving tunnels through the surrounding cloud material and announcing the presence of newly forming stars. Herbig-Haro objects mark the locations where these protostellar jets collide with surrounding cloud material, creating shock-heated knots of glowing gas that move through space like cosmic bullets. Named after astronomers George Herbig and Guillermo Haro, who first studied them systematically in the 1950s. These objects provide direct evidence of ongoing star formation, even when the protostars themselves remain hidden within their dusty birth cocoons. The jets can extend for several light-years from their source, creating vast linear structures that trace the orientation of protostellar rotation axes. The mass accretion process proceeds episodically rather than steadily, with periods of enhanced infall alternating with quieter phases. This variability reflects instabilities in the accretion disk, where gravitational forces compete with magnetic fields and thermal pressure to control material flow. During active accretion episodes, the protostar brightens significantly as gravitational energy converts to thermal radiation. These brightness variations create the characteristic variability observed in young stellar objects throughout their pre-main sequence evolution. Magnetic fields play crucial roles in regulating the accretion process and driving outflow phenomena. The protostar inherits magnetic fields from its parent molecular cloud, and these fields become amplified and twisted as the star contracts and spins up. The resulting magnetic field configuration channels accreting material along field lines that connect the disk to the stellar surface, creating hotspots where matter impacts the protostar at near freefall velocities. The magnetic field also provides the mechanism for angular momentum transport that allows accretion to continue. Without some mechanism to remove angular momentum, accreting material would simply orbit the protostar in the disk without ever reaching the surface. Magnetic forces create torques that transport angular momentum outward through the disk, while allowing matter to spiral inward toward the star. Some of this angular momentum gets carried away by the bipolar jets, helping to solve the angular momentum problem that would otherwise prevent efficient star formation. Different protostellar masses follow distinct evolutionary paths during this phase. Low-mass protostars like our Sun require several million years to complete their accretion phase, gradually building up mass, while their cores slowly heat toward nuclear ignition conditions. High-mass protostars evolve much more rapidly, achieving nuclear fusion while still actively accreting material from their surrounding envelopes. The most massive protostars may begin hydrogen burning within just a few 100,000 years of initial collapse. The transition from first hydrostatic core to true protostar occurs when central temperatures climb above 10,000 degrees Kelvin, hot enough to ionize hydrogen completely and dissociate any remaining molecules. This second collapse phase proceeds more rapidly than the first, driven by the removal of thermal support as ionization absorbs energy. The core contracts by another factor of several hundred, while temperatures soar toward the million-degree threshold required for nuclear fusion. Protostellar evolution during this phase can be tracked through observations of their infrared radiation and molecular line emission. Young protostars appear brightest at far infrared wavelengths, where they radiate the thermal energy generated by gravitational contraction. As they evolve toward main sequence ignition, their spectra shift to shorter wavelengths, and their luminosities stabilize at values determined by nuclear energy generation rather than gravitational contraction. The protostellar awakening represents a critical transition in stellar birth, the moment when a diffuse cloud core becomes a coherent stellar object capable of further evolution toward nuclear ignition. This phase establishes many of the fundamental properties that will characterize the star throughout its main sequence lifetime, including its final mass, angular momentum, and magnetic field configuration. The circumstellar environment, created during protostellar evolution, also sets the stage for planetary formation processes that will continue long after the central star begins nuclear burning. Named after their prototype T Tauri in the constellation Taurus, these young stellar objects represent stars in their cosmic adolescence, no longer embryonic protostars, but not yet settled into main sequence maturity. Like human teenagers, T Tauri stars exhibit dramatic mood swings, unpredictable behavior, and powerful outbursts that announce their presence throughout stellar nurseries. Their tantrums illuminate the complex processes governing pre-main sequence evolution. T Tauri stars occupy a distinct evolutionary phase lasting several million years for solar mass objects. During this period, they derive energy primarily from gravitational contraction rather than nuclear fusion, slowly shrinking and heating, while their cores approach the temperature and density required for sustained hydrogen burning. This quasi-static contraction follows theoretical tracks first calculated by Japanese astrophysicist Chushiro Hayashi in the 1960s, which predict how stellar properties change during pre-main sequence evolution. The variability that characterizes T Tauri stars reflects complex interactions between stellar magnetism, circumstellar disks, and accretion processes. Unlike main sequence stars, whose energy output remains remarkably constant over billions of years, T Tauri stars can change their brightness by factors of several within days or weeks. This variability stems from irregular accretion of disk material onto the stellar surface, creating hotspots that contribute additional luminosity when material impacts the star at high velocities. Classical T Tauri stars actively accrete material from circumstellar disks through magnetospheric accretion processes. Strong magnetic fields, hundreds to thousands of times stronger than the Sun's current field, disrupt the inner portions of the accretion disk at distances of several stellar radii. Material from the disk follows magnetic field lines that connect the disk to the stellar surface, creating funnel flows that channel gas onto specific regions of the stellar photosphere. These accretion shock regions create temperatures exceeding 10,000 degrees Kelvin, where infalling material impacts the stellar surface at velocities approaching 500 kilometers per second. The shock-heated gas emits characteristic spectral lines that betray the presence of ongoing accretion, allowing astronomers to measure accretion rates and study the geometry of magnetospheric flows. The accretion luminosity can contribute significantly to the total energy output of young T Tauri stars, sometimes exceeding the luminosity from gravitational contraction. Weak-line T Tauri stars represent a more evolved phase where significant disk accretion has ceased, but nuclear ignition has not yet begun. These objects show the spectroscopic signatures of youth: strong lithium absorption lines, rapid rotation, and enhanced magnetic activity, but lack the emission lines characteristic of ongoing accretion. The transition from classical to weak-line T Tauri status typically occurs when the circumstellar disk disperses, either through photoevaporation by stellar radiation or removal by stellar winds. Stellar winds from T Tauri stars play crucial roles in dispersing circumstellar material and regulating angular momentum evolution. These winds, driven by magnetic pressure and thermal expansion, remove both mass and angular momentum from the stellar surface. The mass loss rates, though small compared to accretion rates during the classical phase, become increasingly important as accretion declines. Wind speeds typically reach several hundred kilometers per second, sufficient to clear away residual disk material and halt further accretion. The magnetic fields of T Tauri stars exhibit complex geometries that evolve throughout the pre-main sequence phase. Initially, the fields likely reflect the magnetic environment inherited from the parent molecular cloud. As the star contracts and spins up during formation, these fields become amplified and twisted into complex configurations. Dynamo processes generated by convective motions in the stellar interior may also contribute to field generation, creating the strong, variable magnetic fields observed in young stars. Lithium burning serves as a sensitive indicator of stellar interior temperatures during T Tauri evolution. Lithium nuclei destroy through nuclear reactions at temperatures around 2.5 million degrees Kelvin, much lower than the 10 million degrees required for hydrogen fusion. The gradual depletion of lithium in stellar atmospheres thus provides a thermometer for measuring core temperatures as stars contract toward main sequence ignition. The lithium depletion timescale depends on stellar mass, with lower mass stars burning their lithium more slowly due to their cooler interior temperatures. Convective mixing plays important roles in T Tauri stellar interiors, transporting both heat and chemical elements throughout much of the stellar volume. Unlike main sequence stars, which develop radiative cores surrounded by convective envelopes, pre-main sequence stars below about 1.3 solar masses remain fully convective throughout their contraction phase. This complete mixing homogenizes the stellar composition and ensures that lithium burning affects the entire stellar inventory rather than just the core regions. Deuterium burning occurs early in T Tauri evolution, providing nuclear energy when central temperatures reach just 1 million degrees Kelvin. Though the total deuterium inventory is tiny, only about 20 parts per million of the hydrogen abundance. Its destruction releases enough energy to temporarily halt gravitational contraction for objects below 0.8 solar masses. This deuterium burning phase lasts only a few million years, but creates detectable changes in stellar luminosity and surface temperature. The rotation rates of T Tauri stars reflect complex angular momentum evolution during pre-main sequence contraction. While conservation of angular momentum would predict dramatic spin-up as stellar radii decrease, observations show that T Tauri stars rotate much more slowly than expected. This discrepancy indicates efficient angular momentum removal, likely through magnetic coupling between the star and its circumstellar disk, combined with angular momentum loss through stellar winds. Disk-star magnetic coupling creates a scenario where the stellar magnetic field threads through the inner disk regions, forcing disk material to corrotate with the star out to several stellar radii. This magnetic connection transfers angular momentum from the star to the disk, preventing runaway spin-up that would otherwise tear the star apart through centrifugal forces. As the disk disperses, this coupling weakens and stellar rotation begins to accelerate toward main sequence values. Brown dwarf formation represents an alternative evolutionary path for objects that fail to achieve hydrogen fusion temperatures. These failed stars follow similar evolutionary tracks to T Tauri stars during their early phases, but gradually cool over billions of years rather than stabilizing on the main sequence. Brown dwarfs below the deuterium burning threshold never experience nuclear energy generation, while those above this limit exhaust their deuterium within a few million years and then cool steadily. The T Tauri phase establishes many stellar properties that persist throughout main sequence evolution. The final stellar mass depends on when accretion ceases, typically determined by disk dispersal timescales. The stellar rotation rate reflects the angular momentum evolution during the T Tauri phase. Chemical abundances get established through convective mixing and nuclear processing of light elements. Even magnetic field properties may retain memory of processes operating during pre-main sequence evolution. Planet formation processes operate concurrently with T Tauri evolution, creating planetary systems within the circumstellar disks that surround young stars. The timescales for planetary formation, roughly 1 to 10 million years, overlap significantly with T Tauri evolutionary timescales, creating complex interactions between stellar evolution and planetary system architecture. Understanding T Tauri evolution thus provides crucial context for understanding how planetary systems, like our own solar system, formed and evolved during their earliest phases. After millions of years of patient gravitational contraction, stellar cores finally achieve the extraordinary conditions required for nuclear fusion. Temperatures exceeding 10 million degrees Kelvin and densities approaching 10 times that of lead. At this cosmic moment, hydrogen nuclei overcome their mutual electrical repulsion and fuse together, releasing energy that will power stellar burning for billions of years. This nuclear ignition marks the true birth of a star. The journey to nuclear ignition follows a precisely orchestrated sequence governed by fundamental physics. As gravitational contraction slowly increases core temperature and density, conditions approach the threshold where nuclear reactions become possible. The critical temperature of 10 million degrees reflects the balance between electrical repulsion forces that push protons apart and thermal motions that drive them together. Below this temperature, protons lack sufficient kinetic energy to overcome electrical barriers. Above it, fusion proceeds at rates capable of powering stellar luminosity. Nuclear fusion in stellar cores operates through quantum mechanical tunneling, a phenomenon impossible in classical physics but essential for stellar energy generation. Even at 10 million degrees, hydrogen nuclei possess insufficient energy to classically overcome their electrical repulsion. Instead, they tunnel through the electrical barrier through quantum mechanical effects that allow particles to appear on the other side of energy barriers they cannot classically surmount. This tunneling probability depends exponentially on temperature, creating a sharp threshold for nuclear ignition. The proton-proton chain reaction converts hydrogen into helium through a carefully choreographed sequence of nuclear processes. The reaction begins when two protons collide with sufficient energy to overcome electrical repulsion and approach close enough for the strong nuclear force to bind them together. During this collision, one proton transforms into a neutron through beta plus decay, creating a deuterium nucleus, a positron, and a neutrino. This first step represents the slowest link in the fusion chain, determining the overall energy generation rate. Subsequent steps in the proton-proton chain proceed more rapidly once deuterium forms. The deuterium nucleus quickly captures another proton to form helium-3, releasing a gamma-ray photon in the process. Two helium-3 nuclei can then collide and fuse to form helium-4, releasing two protons that become available for additional fusion reactions. The net result converts four hydrogen nuclei into one helium nucleus, with the mass difference converted to energy, according to Einstein's famous equation E equals mc squared. Nuclear binding energy provides the fundamental source of stellar power. When four hydrogen nuclei combine to form one helium nucleus, the helium weighs slightly less than the sum of its constituents, about 0.7% less massive. This missing mass converts entirely to energy, creating the luminosity that makes stars shine. The energy release per fusion reaction is tiny by human standards, but stellar cores contain such enormous numbers of nuclei that collective fusion generates power outputs exceeding all human energy consumption by factors of trillions. The stellar core establishes nuclear equilibrium when energy generation exactly balances energy loss through surface radiation. This equilibrium differs fundamentally from the gravitational contraction that powered pre-main sequence evolution. Nuclear fusion provides a stable, long-term energy source that can maintain stellar luminosity for billions of years without requiring further gravitational compression. The star has finally achieved energy independence, deriving power from its own nuclear resources rather than gravitational potential energy. Hydrostatic equilibrium becomes established when nuclear energy generation provides sufficient thermal pressure to support the star against gravitational collapse. The energy released by fusion reactions heats the stellar material, increasing pressure throughout the star and halting further contraction. This equilibrium condition requires precise balance. Too little nuclear burning and gravity wins, causing continued contraction. Too much, and the star would expand. Self-regulating feedback mechanisms ensure that fusion rates automatically adjust to maintain equilibrium. The star's first nuclear heartbeat establishes rhythms that will persist throughout main sequence evolution. Temperature and pressure in the stellar core oscillate slightly around equilibrium values as nuclear reactions respond to small variations in density and temperature. These oscillations create detectable pulsations in stellar brightness that astronomers can observe in young stars just beginning their nuclear burning phase. The establishment of stable nuclear burning marks the transition from chaotic pre-main sequence variability to the steady luminosity characteristic of main sequence stars. Main sequence lifetime begins at the moment of nuclear ignition and extends until core hydrogen exhaustion forces the star to evolve toward red giant phases. For solar mass stars, main sequence burning continues for approximately 10 billion years, a timescale that dwarfs all previous evolutionary phases combined. More massive stars burn their nuclear fuel more rapidly, completing main sequence evolution in millions rather than billions of years. Lower mass stars burn so slowly that their main sequence lifetimes exceed the current age of the universe. Energy transport from core to surface becomes critically important once nuclear burning begins. The gamma-ray photons produced by fusion reactions cannot escape directly from stellar cores due to the high opacity of stellar material. Instead, they undergo countless absorption and re-emission events as they random walk outward through the stellar interior. This diffusion process requires thousands to millions of years, meaning that starlight observed today was generated by nuclear reactions that occurred when human civilization was just beginning. The establishment of nuclear burning creates distinct internal zones within stellar structure. The nuclear burning core typically extends from the center outward to about 25% of the stellar radius, where temperatures and densities become insufficient for fusion reactions. Surrounding this core, a radiative zone transports energy outward through photon diffusion. Near the surface, a convective zone develops where hot material rises and cool material sinks, efficiently transporting energy to the photosphere where it finally escapes as starlight. Neutrino production accompanies nuclear fusion reactions, creating ghostly particles that escape directly from stellar cores without interacting with surrounding material. These neutrinos carry about 2% of the nuclear energy generation and provide direct information about fusion reactions occurring in stellar interiors. Neutrino detectors on Earth can observe these particles from the Sun's core, confirming theoretical predictions about solar energy generation and providing real-time monitoring of nuclear processes occurring 93 million miles away. The chemical composition of stellar cores begins to change as nuclear burning converts hydrogen into helium. This composition evolution proceeds slowly during main sequence phases, but accelerates dramatically during post-main sequence evolution. The gradual buildup of helium ash in stellar cores increases mean molecular weight and density, slowly altering stellar structure throughout main sequence lifetimes. These composition changes eventually drive the evolution toward red giant phases, when core hydrogen becomes exhausted. Nuclear ignition represents the culmination of stellar birth processes that began with gravitational collapse in molecular cloud cores. The stable energy source provided by fusion reactions enables stars to maintain steady luminosity for timescales comparable to cosmic evolution. This nuclear awakening transforms former cloud material into brilliant cosmic beacons that illuminate galaxies, drive stellar winds that enrich interstellar space, and provide the energy sources that enable planetary formation and biological evolution. The nuclear flame that ignites in stellar cores ultimately powers the entire cosmic web of structure and complexity that characterizes the modern universe. Stars rarely form in isolation. Like human families, stellar birth typically produces siblings, binary systems, multiple star groupings, and vast stellar clusters, where hundreds or thousands of stars share common origins within the same molecular cloud nursery. These stellar families tell stories of shared inheritance, competitive dynamics, and gravitational bonds that can persist for millions or billions of years across galactic space. Binary star formation emerges naturally from the gravitational dynamics governing collapsing cloud cores. As molecular cloud material falls inward under gravity, small asymmetries and turbulent motions become amplified through gravitational instabilities. Dense cores often fragment into two or more condensations, each gathering material from the surrounding envelope while orbiting around their common center of mass. This fragmentation process creates proto-binary systems that evolve together, sharing circumstellar material and experiencing mutual gravitational influences throughout their formation. The statistics of binary formation reveal fundamental insights about stellar birth processes. Observations indicate that roughly half of all solar-type stars exist in binary or multiple systems, with the binary fraction increasing for more massive stars. High-mass stars show binary frequencies approaching 100%, suggesting that massive star formation almost inevitably produces multiple systems. This trend reflects the greater gravitational binding energy of massive systems and their ability to survive dynamical interactions that might disrupt lower-mass binaries. Wide binary systems, with separations ranging from hundreds to tens of thousands of astronomical units, preserve fossil records of initial fragmentation conditions. These systems form when cloud cores fragment on large scales, creating multiple condensations that remain gravitationally bound despite large orbital separations. The wide binaries evolve essentially independently, each component following its own evolutionary track while maintaining their gravitational connection across vast distances. Some wide binaries have orbital periods measured in millions of years. Close binary systems present more complex formation scenarios, where gravitational and magnetic interactions become important throughout the accretion phase. When proto-binary components orbit within a few astronomical units, they can exchange material through gravitational torques and share common circumstellar envelopes. Magnetic field lines may connect the two components, enabling mass transfer and angular momentum exchange that influences the final stellar properties. Some close binaries may form through capture processes or orbital decay of initially wider systems. Contact binary systems represent the extreme limit of close binary evolution, where two stars share common envelopes and exchange material through direct mass transfer. These systems likely form through continued orbital decay of close binaries, possibly driven by magnetic braking or gravitational wave radiation. The resulting stars may have unusual compositions and evolutionary properties due to mixing of material between components during their formation and early evolution. Stellar clusters provide the most dramatic examples of stellar family formation, where single molecular cloud complexes give birth to hundreds or thousands of stellar siblings within a few million years. Open clusters like the Pleiades contain hot, massive stars still surrounded by remnants of their birth nebulae, indicating recent formation within the last few million years. These young clusters preserve the initial conditions of star formation and allow astronomers to study entire stellar populations with common ages and compositions. The initial mass function emerges from competitive accretion processes operating within stellar clusters. When multiple protostars form within the same molecular cloud region, they compete for available material based on their gravitational cross-sections and positions within the accretion flow. More massive protostars tend to accrete material more efficiently, leading to a characteristic mass distribution where high-mass stars are rare and low-mass stars are abundant. This salpeter slope, first identified in the 1950s, appears remarkably universal across different star-forming environments. Dynamical evolution gradually disperses most stellar clusters through internal gravitational interactions and external tidal forces from the galaxy. Young clusters initially remain bound by their mutual gravitational attraction, but stellar motions create small perturbations that grow over time through chaotic dynamics. Two-body encounters between cluster members gradually increase the velocity dispersion until individual stars acquire enough kinetic energy to escape the cluster potential. Most open clusters dissolve within a few 100 million years. Globular clusters represent ancient stellar families that have survived for billions of years through their exceptional gravitational binding. These dense clusters contain hundreds of thousands to millions of stars, packed into regions only a few light-years across. Their extreme densities and large masses enable them to survive tidal disruption and retain their stellar populations throughout galactic lifetimes. Globular clusters preserve fossil records of star formation in the early universe when metallicities were much lower than current values. Stellar associations represent loosely bound groups of young stars that share common space motions and ages, but lack sufficient gravitational binding to remain permanently together. These associations include T associations of low-mass stars and OB associations of massive hot stars, both indicating recent star formation in molecular cloud complexes. The stellar associations expand gradually due to internal velocity dispersions, eventually dispersing individual members throughout galactic space while retaining kinematic signatures of their common origins. The dynamical interactions within stellar families create complex evolutionary scenarios, impossible for isolated stars. Binary stars can exchange material during post-main sequence evolution, creating exotic objects like white dwarf binaries, neutron star systems, and type Ia supernovae. Stellar collisions within dense clusters can produce blue straggler stars that appear younger than their cluster age. Three-body interactions can eject stars from clusters at high velocities, creating runaway stars that stream through galactic space. Hierarchical fragmentation creates nested stellar families, where binary systems exist within larger multiple systems, which themselves may belong to stellar clusters or associations. The Alpha Centauri system exemplifies this hierarchy, consisting of a close binary, Alpha Centauri, A and B, orbited by a distant third component, Proxima Centauri. With the entire system moving through space as part of a larger stellar kinematic group, such hierarchical systems require special formation conditions and dynamical stability to survive over long timescales. The survival of stellar families depends on delicate balances between binding energies and disruptive forces. Internal velocity dispersions, generated by stellar evolution and dynamical interactions, tend to expand and eventually dissolve stellar groups. External tidal forces from galactic gravitational fields and encounters with molecular clouds can strip away loosely bound cluster members. Only the most tightly bound systems survive for billions of years, preserving their stellar families across cosmic time. Observational techniques for studying stellar families include proper motion measurements that reveal common space velocities, spectroscopic analysis that identifies common chemical compositions, and photometric studies that determine common ages and distances. Modern space missions like Gaia have revolutionized our understanding of stellar families by providing precise positions and motions for millions of stars, revealing previously unknown kinematic groups and dissolving cluster remnants scattered throughout the galaxy. The formation of stellar families reflects fundamental aspects of the star formation process: the fragmentation of molecular clouds, the competitive dynamics of gravitational accretion, and the role of initial conditions in determining final stellar properties. Understanding these processes provides crucial insights into galactic chemical evolution, the formation of planetary systems, and the cosmic context within which our own solar system formed as part of an ancient stellar family whose siblings have long since dispersed throughout the galaxy. One of the most profound puzzles in stellar astronomy concerns the seemingly universal pattern of stellar birth weights across the galaxy. Why does nature consistently produce many more low-mass stars than high-mass stars, following a predictable mathematical relationship that appears the same whether stars form in dense clusters or sparse associations, in spiral arm regions or galactic halos? This pattern, known as the initial mass function, reflects fundamental physics governing stellar birth and holds keys to understanding galactic evolution and cosmic structure formation. Edwin Salpeter first quantified this mass distribution in 1955, analyzing stellar populations in the solar neighborhood to derive what became known as the Salpeter slope. His analysis revealed that the number of stars decreases as mass increases, following a power law relationship. For every massive star, approximately 10 stars form with half that mass, 100 stars form with 1/4 the mass, and so forth. This inverse relationship creates stellar populations dominated by low-mass red dwarfs, with hot massive stars representing rare exceptions. The physics driving mass distribution during star formation involves complex interactions between gravitational accretion, thermal pressure, magnetic fields, and stellar feedback processes. As molecular cloud cores collapse and fragment, the resulting protostellar condensations compete for available material within their gravitational reach. This competitive accretion naturally favors objects that form first or in regions of higher density, allowing them to grow larger while preventing smaller objects from accreting efficiently. Brown dwarf formation represents the low-mass end of the stellar mass function, marking the boundary between successful stars and failed stellar objects. Objects below approximately 0.08 solar masses cannot achieve the core temperatures required for sustained hydrogen fusion, condemning them to gradual cooling over billions of years rather than main sequence burning. The brown dwarf population provides crucial constraints on star formation models, as their abundance reflects the efficiency of low-mass object formation in molecular cloud environments. The stellar mass function exhibits a characteristic peak around 0.3 solar masses, below which the number of objects begins to decrease toward the brown dwarf regime. This turnover indicates that star formation becomes less efficient at producing very low-mass objects, possibly due to heating from nearby massive stars that prevents the smallest cloud cores from collapsing successfully. The location of this peak varies slightly between different star-forming regions, suggesting environmental influences on low-mass star formation. Massive star formation presents unique challenges that help explain their rarity in stellar populations. Objects above approximately 8 solar masses face strong radiation pressure from their own luminosity during the accretion phase, potentially halting further mass growth before reaching high masses. Additionally, massive protostars evolve rapidly toward nuclear ignition, beginning hydrogen fusion while still accreting material. This creates complex feedback effects, where stellar winds and radiation pressure from the central object compete with gravitational accretion from the surrounding envelope. The upper mass limit for star formation appears to occur around 150 to 300 solar masses, though very few stars approach this theoretical maximum. Observations of the most massive known stars suggest that radiation pressure and stellar winds become so strong at these masses that further accretion becomes impossible. The exact upper limit may depend on metallicity, with lower metallicity environments potentially allowing somewhat more massive stars due to reduced opacity and weaker radiation pressure. Environmental effects create variations in the initial mass function between different star-forming regions, though the overall shape remains remarkably consistent. Dense stellar clusters tend to produce slightly more massive stars on average, possibly due to competitive accretion effects in high-density environments. Regions of active star formation triggered by supernova explosions or stellar winds may also show enhanced massive star formation due to compression effects that promote rapid accretion onto forming protostars. The metallicity dependence of the initial mass function provides insights into star formation in the early universe, when heavy elements were much less abundant than today. Theoretical models suggest that the first generation of stars, population 3, may have been significantly more massive, on average, due to less efficient cooling in metal-poor gas. The absence of heavy elements reduced the opacity of collapsing clouds, allowing larger Jeans masses and potentially creating a top-heavy initial mass function dominated by massive stars. Feedback processes from massive stars play crucial roles in regulating the overall efficiency and mass distribution of star formation. High-mass stars produce intense ultraviolet radiation, powerful stellar winds, and eventual supernova explosions that heat and disperse surrounding molecular cloud material. These feedback effects can terminate star formation in a given region while triggering new star formation in neighboring cloud complexes through compression and shocking of the interstellar medium. The time dependence of the initial mass function reflects the competition between accretion and feedback processes operating on different timescales. Massive stars form and begin producing feedback effects within a few million years, while low-mass stars require longer accretion timescales to reach their final masses. This temporal evolution can create apparent variations in the mass function as different stellar populations reach different evolutionary phases during the star formation process. Observational techniques for measuring the initial mass function face significant challenges due to the faintness of low-mass stars and the rapid evolution of massive stars. Low-mass red dwarfs require sensitive infrared observations to detect, while massive stars evolve off the main sequence within a few million years of formation. Correcting for these observational biases requires careful analysis of stellar evolution models and detailed photometric surveys across multiple wavelengths. Binary star formation complicates initial mass function measurements since many systems contain two or more stars whose combined light can masquerade as single massive objects. The high binary frequency among massive stars particularly affects measurements in this regime, requiring spectroscopic analysis to identify and resolve individual components. Additionally, dynamical interactions in dense clusters can lead to stellar mergers that create apparent massive stars through collisional processes rather than initial formation. The universality of the initial mass function across different environments suggests fundamental physical principles governing star formation that operate independently of local conditions. This universality has profound implications for galactic chemical evolution, as it determines the relative numbers of massive stars that produce heavy elements through nucleosynthesis and supernova explosions. It also influences galactic energy budgets, as massive stars dominate luminosity outputs despite their small numbers. Understanding the initial mass function requires connecting observations of stellar populations to theoretical models of molecular cloud fragmentation and competitive accretion. Modern simulations can follow the collapse and fragmentation of molecular clouds with unprecedented detail, tracking the formation of individual protostars and their subsequent accretion histories. These models increasingly reproduce observed mass function properties, providing confidence in our theoretical understanding of stellar birth processes. The initial mass function provides a crucial link between local star formation physics and galactic scale evolution. By determining the relative numbers of stars across different mass ranges, it controls the rates of heavy element production, supernova feedback, and stellar remnant formation that drive galactic chemical and dynamical evolution. This connection between stellar birth statistics and cosmic evolution makes the initial mass function one of the most important empirical relationships in all of astronomy, encoding fundamental information about how the universe transforms primordial gas into the complex stellar ecosystems we observe today. The light that emerges from a newly formed star carries within it the story of an extraordinary journey. Energy generated in the nuclear furnace of the stellar core must travel through hundreds of thousands of miles of stellar material, before finally escaping as the starlight that illuminates space. This journey from core to corona represents one of nature's most patient processes, where individual photons undergo millions of interactions across timescales that span from microseconds to millennia. Energy transport within stellar interiors operates through two fundamentally different mechanisms that dominate in different regions of the star. In the deep interior, where temperatures exceed millions of degrees and matter exists as fully ionized plasma, radiative transport carries energy outward through the absorption and re-emission of photons. Near the surface, where temperatures drop below the ionization threshold and convective instabilities develop, bulk motions of stellar material efficiently transport energy through convective cells that operate like vast stellar weather systems. The radiative zone extends from the nuclear burning core outward to approximately 70% of the stellar radius in Sun-like stars. Within this region, gamma-ray photons produced by nuclear fusion reactions begin their tortuous journey toward the surface through countless absorption and re-emission events. Each photon travels only a fraction of a millimeter before encountering an electron or ion that absorbs its energy and immediately re-emits it in a random direction. This random walk process ensures that energy generated in the core diffuses outward at rates much slower than the speed of light would suggest. The photon diffusion timescale represents one of the most remarkable temporal scales in nature. While light can travel from the sun's surface to Earth in just 8 minutes, the same photons required roughly 170,000 years to diffuse from the solar core to the photosphere. This means that sunlight observed today was generated by nuclear reactions that occurred when early humans were developing language and creating the first cave paintings. The stellar interior acts as an enormous energy reservoir that smooths out variations in nuclear energy generation over these vast timescales. Temperature gradients within stellar interiors determine the efficiency of energy transport and the stability of radiative zones. As energy flows outward through radiative diffusion, temperatures must decrease at rates sufficient to maintain the energy flux while remaining stable against convective overturning. When temperature gradients become too steep, radiative transport becomes inefficient, and convective motions develop to carry energy more effectively. The boundary between radiative and convective zones depends on stellar mass, composition, and evolutionary state. Convective zones develop when energy transport through radiation becomes insufficient to carry the nuclear energy flux outward. In these regions, hot material rises from deep layers while cool material sinks from higher levels, creating overturning motions that efficiently transport both energy and chemical elements. The convective velocities can reach several kilometers per second, creating turbulent motions that mix stellar material and homogenize chemical compositions within convective regions. The convective zone structure varies dramatically with stellar mass. Low-mass stars below 0.3 solar masses remain fully convective throughout their interiors, ensuring complete mixing of nuclear products and homogeneous chemical evolution. Solar-type stars develop convective cores during main sequence evolution if their masses exceed about 1.1 solar masses, while maintaining convective envelopes near their surfaces. Massive stars above 1.3 solar masses have convective cores that extend to significant fractions of their total radius. Stellar photosphere formation marks the transition from optically thick interior regions to the transparent atmosphere from which light can finally escape. The photosphere represents the visible surface of the star, though stellar material continues outward into progressively thinner atmospheric layers. The temperature and pressure conditions in the photosphere determine the spectral characteristics observed in starlight and provide the primary observational data for determining stellar properties. The stellar atmosphere extends outward from the photosphere through the chromosphere to the corona, with each layer exhibiting distinct physical properties and energy transport mechanisms. The chromosphere, visible during solar eclipses as a thin reddish layer, shows temperatures that actually increase with height above the photosphere. This temperature reversal indicates additional heating mechanisms beyond simple radiative cooling, likely involving magnetic field effects and wave heating processes. Stellar coronae represent the outermost atmospheric layers where temperatures soar to millions of degrees despite their extreme distance from nuclear energy sources. The coronal heating problem remains one of the outstanding puzzles in stellar physics, with magnetic reconnection events and acoustic wave dissipation among the proposed mechanisms. Coronal material is so hot that it becomes completely ionized and emits primarily X-ray radiation rather than visible light. Magnetic fields play increasingly important roles in stellar atmospheres, where gas pressures become low enough for magnetic pressure to dominate. These fields, generated by dynamo processes in stellar interiors, emerge through the photosphere and create complex magnetic structures that channel energy, flow, and drive atmospheric heating. Solar observations reveal magnetic field concentrations that create sunspots, coronal loops, and solar flares that demonstrate the dynamic nature of stellar magnetic atmospheres. Stellar winds originate in the hot coronae, where thermal velocities exceed the stellar escape velocity. The combination of high temperatures and low densities allows charged particles to stream away from the star along magnetic field lines, creating mass loss rates that can significantly affect stellar evolution over long timescales. These winds carry both mass and angular momentum away from the star, influencing rotation rates and evolutionary paths. The development of stellar classification systems in the early 1900s revealed systematic relationships between surface temperatures, colors, and spectral characteristics. The Harvard classification scheme, refined by Annie Jump Cannon and her colleagues, organized stellar spectra into a temperature sequence running from hot O-type stars through cool M-type stars. This classification revealed that stellar surface properties depend primarily on mass and evolutionary state, providing the foundation for understanding stellar structure and evolution. Stellar oscillations and pulsations provide powerful probes of stellar interior structure through asteroseismology techniques, analogous to terrestrial seismology. Just as earthquake waves reveal Earth's internal structure, stellar oscillations carry information about temperature, density, and composition gradients throughout stellar interiors. Modern space missions can detect oscillation periods and amplitudes with sufficient precision to map stellar interior structure in unprecedented detail. The transition from nuclear core to visible photosphere establishes the basic stellar structure that will persist throughout main sequence evolution. The energy transport mechanisms, atmospheric properties, and magnetic field configurations developed during stellar birth influence observational characteristics and evolutionary paths for billions of subsequent years. Understanding these interior processes provides crucial insights into stellar physics and enables astronomers to interpret the diverse properties observed in stellar populations throughout the galaxy. Star formation operates as a universal process throughout cosmic history, yet the environments where stars are born have evolved dramatically since the universe's earliest epochs. From the massive population 3 stars that formed in primordial gas clouds, devoid of heavy elements, to the ongoing stellar birth in metal-enriched molecular clouds within modern spiral galaxies. Stellar nurseries across the universe reveal the changing conditions that govern cosmic evolution and galactic chemical enrichment. The very first stars in cosmic history formed under conditions radically different from modern star formation environments. Population 3 stars, born when the universe was only a few 100 million years old, formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium created during Big Bang nucleosynthesis. Without heavy elements to provide efficient cooling mechanisms, these primordial molecular clouds remained hotter during gravitational collapse, leading to higher genes masses and potentially more massive stars than typical modern stellar populations. The absence of dust grains in primordial environments eliminated many of the cooling processes that enabled present-day star formation. Modern molecular clouds rely on carbon monoxide and dust grain surface chemistry to radiate away thermal energy during gravitational collapse. Population 3 star formation instead depended on molecular hydrogen cooling, which operates less efficiently and only at higher densities. These conditions likely produced a top-heavy initial mass function, dominated by massive stars that lived brief lives and exploded as supernovae, enriching the interstellar medium with the first heavy elements. Population 2 stars represent the second generation of stellar formation, occurring in gas clouds enriched by heavy elements from population 3 supernova explosions. These stars, found primarily in globular clusters and galactic halos, formed when metallicities were still much lower than current values, but sufficient to enable more efficient cooling and lower mass star formation. The chemical compositions of ancient population II stars provide fossil records of nucleosynthesis in the first stellar generations and constrain models of early galactic chemical evolution. Modern population I stars, including our Sun, form in metal-enriched environments where heavy elements comprise about 2% of the total mass. This metallicity enables efficient cooling through carbon monoxide emission and provides dust grains that facilitate molecular hydrogen formation and additional cooling processes. The resulting star formation proceeds more gradually with lower characteristic masses, producing stellar populations dominated by low-mass stars capable of main sequence lifetimes exceeding the current age of the universe. Starburst galaxies represent extreme examples of enhanced star formation occurring at rates hundreds of times higher than typical spiral galaxies. These events can be triggered by galaxy mergers that compress molecular clouds and drive massive gas inflows toward galactic centers. The resulting star formation episodes can convert significant fractions of available gas into stars within just a few million years, creating brilliant blue galaxies visible across cosmological distances. Such starbursts may represent typical star formation modes in the early universe when galaxy merger rates were much higher. Environmental metallicity effects create systematic variations in stellar birth characteristics across different galactic regions and cosmic epochs. Higher metallicity environments tend to produce more efficient star formation through enhanced cooling, but also stronger stellar winds and radiation pressure that can disrupt accretion processes. Lower metallicity regions may favor more massive star formation due to reduced opacity and feedback effects, but also suffer from less efficient cooling that inhibits low-mass star formation. Galactic location influences star formation through variations in gas density, metallicity, and external pressure from stellar feedback and spiral density waves. Stars forming in the dense central regions of galaxies experience higher pressure environments that can trigger formation, while also subjecting newborn stars to intense radiation fields from nearby massive stellar populations. Star formation in galactic outskirts occurs in lower density, lower metallicity environments that may favor different initial mass functions and stellar birth characteristics. The cosmic star formation rate has evolved dramatically throughout universe history, peaking at redshifts around 1 to 3 when the universe was 2 to 6 billion years old. This cosmic noon epoch corresponds to the era of most active galaxy formation and merger activity, when gas reservoirs were more abundant and galaxy interaction rates were higher. Since this peak, the global star formation rate has declined by more than an order of magnitude as gas supplies have been depleted and feedback processes have become more effective at regulating star formation. Triggered star formation creates spatial and temporal correlations in stellar birth across galactic scales through feedback-driven processes. Massive stars produce stellar winds, ionizing radiation, and eventual supernova explosions that compress neighboring molecular clouds and trigger additional star formation episodes. These cascade effects can propagate across hundreds of light years and persist for tens of millions of years, creating star formation complexes and associations that reveal the interconnected nature of stellar birth processes. Different galactic morphologies exhibit distinct star formation patterns that reflect their structural and dynamical properties. Spiral galaxies concentrate star formation in spiral arms, where density waves compress molecular clouds and trigger enhanced stellar birth rates. Elliptical galaxies typically show little ongoing star formation due to hot gaseous halos that prevent cooling and molecular cloud formation. Irregular galaxies often exhibit more chaotic star formation patterns, driven by tidal interactions and internal dynamical instabilities. Observational techniques for studying star formation across cosmic distances rely primarily on emission signatures from hot young stars and surrounding nebular gas. Ultraviolet radiation from massive O and B stars ionizes surrounding hydrogen, creating H2 regions that emit characteristic recombination lines detectable across cosmological distances. Far infrared emission from dust heated by young stars provides another tracer of ongoing star formation, particularly in dusty environments where optical emission is heavily obscured. The future evolution of cosmic star formation depends on the continued availability of gas reservoirs and the efficiency of feedback processes in regulating stellar birth rates. Current observations suggest that star formation rates will continue declining as galaxies exhaust their gas supplies through star formation and feedback-driven outflows. The universe appears to be transitioning from an era dominated by active star formation to one characterized by stellar evolution and the gradual formation of stellar remnants. Understanding star formation across different environments and cosmic epochs provides crucial insights into galaxy evolution, chemical enrichment, and the formation of planetary systems. The diversity of stellar nurseries throughout the universe reflects the complex interplay between gravitational collapse, thermodynamic processes, and feedback mechanisms that operate under varying conditions of density, temperature, and chemical composition. These variations ultimately determine the characteristics of stellar populations and their contributions to galactic evolution and cosmic chemical enrichment. The moment when nuclear fusion finally stabilizes in a stellar core marks the true dawn of stellar existence. The transition from gravitational contraction to nuclear burning creates the first steady starlight that will illuminate space for billions of years. This nuclear awakening transforms former cloud material into brilliant cosmic beacons, whose spectral signatures reveal fundamental stellar properties and provide the observational foundation for understanding stellar physics and galactic evolution. Photosphere formation represents the emergence of visible stellar light from the optically thick stellar interior. As nuclear energy generation stabilizes, thermal energy diffuses outward through radiative and convective processes until it reaches layers thin enough for photons to escape directly into space. The photosphere marks this critical transition, the visible surface of the star, where optical depth drops to unity and light finally breaks free from its millions-year journey through stellar material. The formation of stellar spectra provides the primary observational signature that distinguishes newly formed main sequence stars from their protostellar predecessors. Nuclear burning creates stable temperature and pressure conditions throughout stellar interiors, establishing well-defined photospheric temperatures that determine which spectral lines appear in stellar light. The hydrogen-Balmer series, metallic absorption lines, and molecular bands that characterize stellar spectra reflect the physical conditions in stellar atmospheres and provide direct measurements of stellar properties. Stellar classification systems organize the diversity of stellar spectra into a coherent framework that reveals underlying physical relationships. The Morgan-Keenan system, developed in the 1940s, refined the earlier Harvard classification to create the modern OB-FGKM sequence that organizes stars by surface temperature. Each spectral class exhibits characteristic absorption line patterns that reflect ionization states of different elements in stellar atmospheres, providing a direct connection between observable spectra and fundamental stellar physics. O-type stars represent the hottest and most massive main sequence objects, with surface temperatures exceeding 30,000 degrees Kelvin and luminosities thousands of times greater than the Sun. These blue giants show spectra dominated by highly ionized helium and hydrogen, reflecting the extreme conditions in their atmospheres. Despite their impressive luminosity, O-type stars comprise less than 0.001% of main sequence stellar populations due to their rarity in the initial mass function and their brief main sequence lifetimes of only a few million years. B-type stars continue the hot star sequence, with surface temperatures between 10,000 to 30,000 degrees Kelvin and characteristic blue-white colors. Their spectra show strong hydrogen absorption lines, along with singly ionized helium, creating the classic features that define early-type stellar spectra. B-type stars include many familiar bright stars like Rigel and Spica, whose high luminosities make them visible across large distances despite their relative rarity in stellar populations. A-type stars bridge the gap between hot, massive stars and solar-type objects, with surface temperatures around 7,500 to 10,000 degrees Kelvin, producing white or blue-white colors. The hydrogen-Balmer lines reach maximum strength in A-type spectra, while the first metallic absorption lines begin to appear as atmospheric temperatures become cool enough to prevent complete ionization of heavier elements. Sirius, the brightest star in Earth's night sky, exemplifies the A-type class with its brilliant white light and prominent hydrogen features. F-type stars represent late-type objects similar to the Sun, but slightly hotter and more massive, with surface temperatures between 6,000 to 7,500 degrees Kelvin. Their spectra show weakening hydrogen lines, accompanied by strengthening metal lines, particularly calcium and iron absorption features that become increasingly prominent as surface temperatures decrease. F-type stars often serve as analogues for solar evolution, representing what the Sun might have looked like in its youth or will become in its future. G-type stars include the Sun and other solar analogues with surface temperatures between 5,200 to 6,000 degrees Kelvin and characteristic yellow colors. The solar spectrum, studied in extraordinary detail, shows thousands of absorption lines from hydrogen, metals, and molecules that provide templates for understanding stellar atmospheres. G-type stars represent optimal targets for searching for Earth-like planets due to their stable, nuclear-burning, and moderate radiation environments. K-type stars continue toward cooler temperatures between 3,700 to 5,200 degrees Kelvin, displaying orange colors and spectra increasingly dominated by metal absorption lines. Molecular bands, particularly from titanium oxide, begin to appear in the coolest K-type atmospheres, where temperatures become low enough for chemical bonding to survive. These stars comprise a significant fraction of main sequence populations and offer extended main sequence lifetimes that provide stable environments for planetary system evolution. M-type stars represent the coolest and lowest mass main sequence objects, with surface temperatures below 3,700 degrees Kelvin producing distinctive red colors. Their spectra are dominated by molecular absorption bands, particularly titanium oxide features that create the characteristic appearance of red dwarf spectra. Despite their faintness, M-type stars comprise roughly 75% of all main sequence objects and possess main sequence lifetimes measured in hundreds of billions of years. Main sequence positioning reflects the fundamental relationship between stellar mass and luminosity established by nuclear burning equilibrium. More massive stars achieve higher core temperatures and pressures that drive nuclear fusion rates exponentially higher, producing correspondingly greater luminosities. This mass-luminosity relationship spans 6 orders of magnitude, from the least massive red dwarfs to the most massive blue giants, creating the diagonal main sequence band that dominates stellar population diagrams. Nuclear burning patterns vary systematically with stellar mass, creating different internal structure and evolution patterns across the main sequence. Low-mass stars below 0.4 solar masses burn hydrogen exclusively through the proton-proton chain reaction and remain fully convective throughout their interiors. Intermediate-mass stars like the Sun develop radiative cores surrounded by convective envelopes. High-mass stars above 1.3 solar masses operate convective cores and may also utilize the CNO cycle for more efficient hydrogen burning. Stellar lifetime predictions follow directly from nuclear burning rates and available hydrogen fuel supplies. Low-mass red dwarfs consume their hydrogen so slowly that main sequence lifetimes exceed 100 billion years, longer than the current age of the universe. Solar-type stars burn for approximately 10 billion years before exhausting core hydrogen. Massive blue giants consume their nuclear fuel in just a few million years, rushing through main sequence evolution and exploding as supernovae, while low-mass stars have barely begun their nuclear burning phase. Variable stars and stellar pulsations reflect internal processes that create periodic changes in stellar luminosity and surface properties. Classical Cepheid variables undergo regular pulsations driven by opacity changes in helium ionization zones, creating period luminosity relationships that serve as cosmic distance indicators. Other variable star types, including RR Lyrae stars and Delta Scuti stars, result from similar pulsation mechanisms operating in different stellar masses and evolutionary phases. Modern astronomical observations have revolutionized our ability to detect and study newly formed stars through multi-wavelength surveys that reveal stellar births across the electromagnetic spectrum. Space telescopes operating in infrared wavelengths can penetrate dusty stellar nurseries and observe protostars during their earliest evolutionary phases. X-ray observations detect the magnetic activity signatures of young stars, while optical surveys monitor the photometric variability that characterizes pre-main sequence objects. The emergence of stellar light marks the culmination of star formation processes that began in cold molecular clouds millions of years earlier. The nuclear flames that ignite in stellar cores create the energy sources that power galactic evolution, heavy element production, and ultimately, the complex chemistry required for planetary formation and biological evolution. Understanding stellar birth and early evolution provides the foundation for comprehending how the universe transforms primordial hydrogen into the rich tapestry of elements and structures that characterize the modern cosmos. As we reach the end of our journey through the cosmic nurseries where stars are born, we find ourselves witnesses to the universe's most fundamental creative act. From the cold darkness of molecular clouds through the patient compression of gravity, from the first nuclear fires to the emergence of brilliant starlight, we have observed the transformation that connects empty space to shining suns. This process of stellar birth represents more than mere astronomical phenomena. It embodies the universe's inherent drive to create complexity, beauty, and ultimately the conditions necessary for life itself. Each star emerges as a unique fingerprint of its birth environment, carrying within its structure and composition the chemical signature of the molecular cloud from which it formed. The isotope ratios, established during cold chemistry in stellar nurseries, persist throughout main sequence lifetimes, creating traceable connections between stellar birth conditions and observable stellar properties billions of years later. Modern spectroscopy can decode these chemical fossils, allowing astronomers to reconstruct the environments where ancient stars formed and trace the evolution of galactic chemical composition across cosmic time. The continuous cycle of stellar generations creates an elegant cosmic recycling program that enriches the universe with heavy elements essential for planet formation and biological evolution. Massive stars born in one generation live brief but brilliant lives, fusing light elements into heavier ones in their nuclear cores before exploding as supernovae that disperse these newly created elements throughout space. These stellar ashes become incorporated into subsequent molecular clouds, providing the raw materials for new stars, planets, and potentially life in endless cycles of cosmic renewal. Our own solar system exemplifies this stellar inheritance, formed roughly 4.6 billion years ago from molecular cloud material enriched by countless previous stellar generations. The heavy elements that comprise Earth's rocky surface, the carbon in our bodies, and the oxygen we breathe, were forged in the nuclear furnaces of stars that lived and died before our sun was born. We are literally made of stellar material, connected through chains of nucleosynthesis to the very first massive stars that enriched primordial hydrogen with heavier elements. The gentle emergence of light from darkness that characterizes stellar birth reflects deeper principles about how complexity arises in the universe. Rather than sudden violent creation, star formation proceeds through patient processes operating across millions of years, where small gravitational advantages accumulate into profound transformations. This gradual approach ensures that stellar birth occurs continuously throughout galactic history, rather than in catastrophic bursts that would quickly exhaust available raw materials. The future of star formation in our galaxy extends far into cosmic time, though at ever-decreasing rates, as molecular cloud material becomes progressively depleted. Current star formation rates suggest that the Milky Way contains sufficient gas reservoirs to continue producing new stars for several billion more years, though at rates much lower than during peak galactic activity epochs. The lowest mass red dwarf stars forming today will continue shining for hundreds of billions of years, outliving not only our sun but potentially the galaxy itself. Every photon of starlight carries within it the story of nuclear birth, energy generated in stellar cores through the fusion of primordial hydrogen into helium, transported slowly through stellar interiors across thousands of years, and finally released as the light that illuminates planetary surfaces and enables photosynthesis. The warm sunlight that powers life on Earth represents the direct nuclear heritage of stellar birth processes, connecting biological evolution to cosmic nucleosynthesis through chains of energy flow that span from stellar cores to living cells. Stars serve as bridges between the universe's past and future, transforming the primordial hydrogen created during Big Bang nucleosynthesis into the complex elements required for rocky planets and biological chemistry. Without stellar nucleosynthesis, the universe would remain forever dominated by hydrogen and helium, lacking the chemical complexity necessary for solid objects or life. Stellar birth thus represents a crucial step in cosmic evolution that enables the emergence of planets, chemistry, and ultimately consciousness that can contemplate its own origins. The universe continues giving birth to new light in stellar nurseries scattered throughout every galaxy, each new star representing another nuclear flame that will burn for millions to billions of years. In regions like the Orion Nebula, visible in winter skies, star formation actively proceeds at this very moment, creating stellar siblings that will illuminate space long after human civilization has evolved beyond recognition. These ongoing stellar births ensure that the universe remains vibrant and dynamic, rather than gradually fading as older stars exhaust their nuclear fuel. As your consciousness drifts towards sleep, carried by the rhythm of your breathing and the gentle pull of rest, remember that you float within a universe, perpetually giving birth to new stars. The atoms in your body were forged in stellar cores. The energy that powers your thoughts ultimately derives from nuclear fusion, and the light that will warm tomorrow's dawn carries stories of stellar birth from the sun's nuclear heart to your retina. In the cosmic nurseries where starlight is born, the universe writes its autobiography in nuclear fire and gravitational sculpture. Each star represents a chapter in this ongoing story of transformation, where simple hydrogen becomes complex elements, where cold clouds become brilliant beacons, and where darkness inevitably gives way to light. Thank you for joining this exploration of stellar birth through the gentle cosmic nurseries, where stars emerge from dust and darkness into brilliant light. Like and subscribe to Whispering Universes channel for more journeys into the profound mysteries of cosmic creation. Let the warmth of ancient starlight guide your dreams tonight, and remember that every breath you take connects you to the nuclear fires that illuminate the universe. Sleep under ancient light, dream of stars yet to be born.